Hi, so this is the human computer workshop. We'll introduce digital logic circuit. So what this is basically what is inside every single computer, every single mobile phone, every single electronic device you can think of is made up of digital logic circuit at some level. And so what we'll do is introduce what the different type of logic gates are and how they work and how we can implement it with basically anything that's able to make a decision. So um, we're assuming that there's 64 person coming at the workshop. We've got them laid out as follow. So you'll receive a number and you can sit down with this is the where the instructor is the front of the class. This is the first row, second row, third row, etc. up to the last row of the class. And so all the numbers should be lined up in the same ways, and people should be sitting in the same ways that is indicated on this map. Now you'll have three pieces of equipment. The first two are party hats. Nice little party hats with two different colors. In our case, they're blue and gold. So the blue hat, and just this will become clearer later, but means off, 0, 0, or low. So remember, when you see a 0, it's a blue hat. Gold hat is, on the other hand, on, 1, 1 high. So either one of those. So when we say on, you wear the gold hat. When we say off, you wear the blue hat. So just remember those mapping between the colors. So blue hat typically 0, gold hat 1. And because we're talking about digital logic, digital is 0 or 1. You'll also have a numbered bib that you can wear. Make sure the number is pointing backward toward the back of the class so that other people can see your number looking from the back. Now, let's jump to the basics. So at the most basic, before we talk about digital logic, we can talk about electronic circuit. So a very simple electronic circuit is the source of electricity and a switch and a light. In this case, so we're using number 1, so bib number 1, ID number 1 as a toggle, and out is simply basically the output of the circuit. So what happens here is at the moment, out is off, so it's 0, so it's low. So all these have the same meaning here in digital logic. If I toggle, it turns on. It becomes red here. So red in this case means on. Off, on, off, on. So very easy to understand. So you also have something to connect. So if you want to go further distances, there's something called a wire. So the wire only takes the input exactly as it is and outputs it on the other side, while out just lights up based on in or out, right? So up, on, off, on, off, on, off. So very easy to understand. So when you see these symbols, remember, if you're number 1 and you're in, then you will be given if you should be on, off, or on, off or on. If you're number 2 in this case, if you're a wire, then all you need to do is look at number 1 and take the same value as number 1 and wear the same hat and then have it so that the next person looking at you can see the color of the hat. Now if you're out and you're connected to 2 and 2 is connected to 1, so 1 in this case is going to be on, wire is going to be on, and then output is going to be on. So this is the basic principle of electric circuit, right? So we're just translating that into the class and building simple circuits based on that. So wires. So let's do an example with wires. So if the whole class is laid out correctly, you should be able to basically give a value to number 1, either off or on. So if we tell 1 to be off, wear the blue hat. And then wire 9 is looking at 1, so it also should be wearing the blue hat. And 17 is looking at 9, should also be wearing the blue hat. And so it goes until the end. Now, if we tell to input 1 to wear a gold hat, which means on, then you'll see that every single wire takes the same value up to the end, which is the output, which also should be wearing the gold hat, right? So if we keep going like this for every single column here of the class, then we can see that we can turn on every single person at the end. And all they need to look at is one other person to follow the signal. So that's the wire. So the wire is basically just a copy of the value. There's no action. But we'd like to do something a little bit more intelligent, so we'll introduce Boolean. So Boolean, instead of just being a simple dummy wire, we want to do some logic, right? Based on one or more inputs. Now there's 4 fundamental building blocks that we'll introduce one by one. So there's the NOT logic gate, which has this thing called a truth table. So a truth table has on one side all the possible values combination. Since we're talking about digital logic, there's only 2 combinations possible for one bit, 0 and 1. And NOT is very simple in the sense that it takes an input and just inverts it. So if the input is 0, the output will be 1. If the input is 1, the output will be 0. So very simple. And on the other end, basically, is only 1 when both of its input are 1. Or is only 0 if both of the inputs are 0. And XOR, you'll notice, will only be 1 if both input are different. So 0 XOR 1 is 1, 1 XOR 0 is 1. Exclusive OR. Let's go in more detail. So let's try a NOT logic gate. So as we said, we invert the input, whatever it is, right? So it's 2 different inputs, 0 or 1. So if I have a source of electricity, I have this set as a gate, and I have a NOT and then the light. So as you see, the input right now is basically off, meaning the blue hat. So you can imagine in this case, number 1 is wearing a blue hat. And already the hat is on because it's been inverted. So this was 0, NOT turned it into a 1, and this output is reading from the NOT there, right? So if I can disconnect it and reconnect it. Here we go. If I turn this on, what happens? Well, it turns off, right? Because now this is on. This is going to switch it to off and goes to the out and is off. So we can try this exercise as a class. So this is very similar to the wire, except each block is going to invert the signal. So what happens here is if I click on this, this is on, off, on, off, on, off, on, and it goes to out as on, right? So the last one is on, so this is on. If I do the same, and same, right? So very easy to understand. So if the input is 0, turn it to 1. If the input is 1, turn it to 0. So that's the NOT. And it has a single input. Now let's see another example where there's 2 inputs. Now the person that is acting as an OR, or number 3 here, needs to be looking at 2 different persons to determine its output. So in this case, in can be 1 or 0, in 2 can be 1 or 0, and at this point they're both off. They're both 0. So if I turn this one to on, you can see OR turns to on. Why? Because whenever either value is to 1 or both value are to 1, the output will be 1. The only case where it's not is when both are 0. If I turn both on, it's on. If I turn one off, one on, it's on. If I turn this one off and this one on, it's still on. So you can see this is described in the truth table again. Now we can try as a class. So this is a little bit more complex, but you'll see that this has an interesting effect that if everyone in the class is on, it's very quickly, if I turn this on, you can see the progression. And even before I get to the last one, it's already all on. Why? Because even this one is being read by the last row. So its output is going to be 1 and it propagates to the end even if I haven't turned the last one on. And so this is an interesting effect. So what to remember is OR will only be 0 if both input are 0. Now N is a little bit more restrictive. N is actually, its truth table is that both inputs need to be 1 for it to be 1. So in this case, of course, as OR, if both are turned off, the output is off. 0, 0, 0, right? If I turn 1 on, oh, it doesn't turn on because it expects both to be on. So let's turn both on. And then, yes, I do have this output. And if we try it with the whole group, we'll see that it takes quite a bit of time before actually even a single output turns on, right? So you can see that in this case only up the next to last one do we have this one turned on, because there's kind of a diagonal effect going on here. If I turn this one on, then they all turn on because every value is 1. So it propagates all ones and gets to the end and gets 1. So not too difficult to understand. So let's keep going. So XOR, quite interesting effect. A little bit more. You can see that even with simple digital logic, this has interesting combination where if they're both the same, we output 0. If they're 1, 0, 0 is 0, 1 and 1 is 0. But if the bits are different at the entry, we put 1, right? So only when are they different do we have a true value. So we do the same here. So if I put in 1, I get 1. Okay, so they're different. This one is 1, this one is 0, this one is on, this one is off. So the output is 1. Now if I turn both off, again, if I turn this one on, they're different. This is on. If I put both on, then because they're the same, 1 and 1, I do get 0 in this case. And now the XOR, so it has a quite difficult to figure out effect, because depending, you'll see, very kind of, it has like a counter effect. So it depends on the number of XOR gates and how they do their inputs, but it's a quite interesting piece of gate logic. So why do we learn all these gates is because we'll need at least 2 of them to implement a 1-bit half adder, right? So in this case, you'll notice that these 2 columns are actually, or 2 rows, reading it from the screen, are actually only connected to each other through a XOR, exclusive OR, and an AND, right? So the XOR is connected to the first one and the second one. The AND is connected to the first one and second one. And this is repeated because we have 8 rows it's repeated 4 times, right? So this is just to demonstrate 4 different bit adders, so you may understand how they work. So if let's say in this case I want to add 2 bits, right? So 2 bits, so of 1 bit to 1 bit. So I can do 0 plus 0. Of course, the output is going to be 0, right? If I add a 1 to a 0, I get a 1.